Hello, everyone. My name is Dalibor Blažević, and I'm a principal solution architect at Segal and a Kafka evangelist. I had several talks at different Kafka summits, and now I'm here going to present, I hope, something interesting for you at this meetup. So today we are going to talk about Kafka transaction support. So traditionally, we think about Kafka as a streaming system, the system that is able to convey messages from A to B in the streaming fashions, usually messages connected with log outputs or some IoT data or GPS positions. Usually, we don't think that such a system is capable of handling typical transactional actions like processing payments or orders or something similar. But it does, as we are going to see that. So Kafka does enable us to support also this kind of processing as well. So why transactions anyway? Well, in a transactional world, we want that something goes or it's rolled back. So we want that every piece of transaction processing goes or it's rolled back. So we want to avoid duplication. We want to have a guaranteed delivery. And we want to have some form of error handling that is going to allow us to roll back a transaction. So let us examine some real-life integration pattern that we are going to use in this case to explain how the transaction in Kafka works. In some real-life scenario, we usually have some source of data, let's say a front-end or UI that sends the data to a backend. Then we have some data transformation, then some data enrichment, and potentially in that process, we are also calling some external service. And then we are storing, let's say, data in the database. Let us see how this works in a synchronous world. Well, in a synchronous world, that's fairly easy, I would say. So we have a transaction initiator that sends a request, and the same transaction initiator is usually the process that is also responsible for committing or rolling back a transaction. So it sends a request to the data transformation service. This in turn sends the request to the data enrichment service, and this data enrichment service calls an external service. Gets a response, enrich the data, and then we save the data in the database. And then the database commits the data, sends the acknowledgement. We send the acknowledgement back to the transaction initiator. So what can potentially go wrong here? Yeah. Well, every of these services can produce an error or a timeout. And in this case, a transaction initiator will initiate a rollback process. And that's fairly easy with these services because none of them has saved data in the local store. Usually they keep them just in memory. Only the destination has to be rolled back. However, what about this external service? Yeah, that might be a problem. So not everything goes in that scenario. We don't have any responsibility of the external service. We are not able to roll back it easily. So let us observe a little bit this scenario in which we have already committed data to an external service, and then we try to save this data in a database and it fails. So we have to roll back everything. We know that rollbacking data in database is quite easy, but what about that external service? Typical solution in that scenario, in integration world, is to implement something that we call for a compensation action. That means that we have to implement some form of a deletion process. So when we want to roll back also external service, we will effectively send a delete command to that external service to delete already committed transaction. And this works not just for external services, that is a typical example. This also works for many internal cases as well, when we cannot simply send a rollback command and rollback things that we done. So we have to think about that as well. And this works also in a case of Kafka as well in some scenarios. Well, Let us now see the same scenario, but asynchronously. In asynchronous world, things get far more complex. Why? First of all, because of the transaction boundaries. So usually the same process that initiated the transaction is not the same process that is going to end transaction. So this process that initiates transaction is usually a producer, or we call it a producer. And the process that ends the transaction is a completely different process. It's called consumer. So you can see the transaction now boundaries are set in an asynchronous fashion. Moreover, we have a numerous points in which we are effectively storing the state of the data. In the Kafka world, we call them topics. And moreover, we are also very often sending data in batches. So we are not sending individual messages, but the batch of messages. Why we do that? Well, for efficiency reason. We want to speed up the process, and that's why we do it. But as you can see, this makes a transactional processing far more complex. So what the headache we have in distributed world? Well, we do not have just to think about implementing compensation messages. We always do that. But we also have to see how to deal with duplicates. For example, data producer, when not receiving an ACK or a timeout, it actually will retry, and then we have duplicate writes. Or a lead broker receiving error from in-sync replica, and again, it will result in duplicate writes. We will see that in more details. Or data consumer reading twice. When I say not only compensation, well, when we want to implement transactional support in an asynchronous world, we also have to think about implementing response topics. So the topics that we use as different channels to send responses, error topics to send errors, cleanup policies, how to deal with timeout in each service. So not just on the producer or the transaction initiator, but in each and every service. Because it's not synchron. I'm not going to explain in detail here how that can be achieved. I had a talk on a Kafka Summit 2 years ago, so please have a look at that if you want to learn more, because we don't have time right now to explain that in details. So let us see now how duplicate writes can happen and when it occurs. Let's see a scenario in which a producer sends a message to a broker. And of course, the broker writes that message to a topic. And unfortunately, broker dies before sending an acknowledgement. And then timeout occurs. The producer will then retry the message. Let's say it will try to send it to another broker, or the same broker has restarted. The message is then written again to a broker, and broker writes it again to a topic, and effectively this results in duplicate messages. Now the correct acknowledgement is sent back, but it's a little bit too late because we ended up with two messages in the topic, two equal messages. Another scenario when this can happen is that when the producer sends a message to a lead broker, then because of the high availability, we want to duplicate that message, not just by saving it to topic, but also by sending it to in-sync replica broker. And then, unfortunately, this replica broker dies before sending us an acknowledgement. And because we want to have acknowledgement of all brokers, the lead broker is forced to send an in-sync replica error, which effectively forces the producer to retry the message. And then what happens? Again, duplicate message is written to a topic. Well, not quite a desirable state for us if we want to support transactions. So how Kafka solve these duplicate write problems? Well, there are two things that the Kafka uses. One is independence, another is support for atomic write across multiple partitions. So how to enable idempotence? That's fairly easy. We just set a property enable idempotence to true in the broker server properties, and then we restart the broker. What this effectively does is adds additional piece of information with every batch of messages that's going to be sent to a broker, and that is a batch sequence number. So the sequence number is persisted to the replica log, and this replica log is available to all brokers. So all brokers will know when the same batch is attempted to be being sent twice, and this batch is going to be discarded, thus not going to be written to a topic. Another thing that broker has is a parallel process, or a separate process that is called transaction manager. So we will see a little bit later how the transaction manager works, but it's important to know that this transaction manager allows us to send messages in a fashion or everything goes or everything is rolled back. So we can initiate a transaction by using init transaction API, and then we begin transaction, and everything that is sent within the transaction boundaries is either committed or either marked as aborted if some exception occurs. So how we enable transactional manager support on the producer side? Well, that's easy. Just by adding another property that is called transactional ID. And this has to be set to unique string. Any unique string will do. And the same thing if we are using Kafka Stream services, we set process guarantee property to exactly once. So under the hood, it will achieve the same thing. This enables producer to communicate with the transactional manager. And one of the features that this allows us to have is so-called zombie phasing. What that means? That means that whenever a transaction manager realizes that there are two producers with the same transaction ID, one of them is going to be phased out. So only one producer with the same ID is allowed. All others are fenced out. How that is done? Well, each producer, in addition to transactional ID, is also sending an epoch. So with each message, an epoch is increased. And if another producer, let's call it a zombie, is sending the same package with the same transaction ID, but with an older epoch, this zombie producer is effectively fenced out. So let's see a little bit more in detail how this transaction coordinator works. So the transaction coordinator, when we call this initiate transaction, is effectively is going to effectively establish a link between the producer and itself, and it's going to register a partition to which the producer is trying to, or partitions to which the producer is trying to write with itself. Then the transaction coordinator is going to use its internal log or a topic, its internal topic, to write the state of each batch of messages that are coming from the producer. So we can see that the first is initializing state, then it's ongoing, then it's prepare when it's almost ready, and then we have a commit. Then in the phase C, the producer writes as usual. However, transaction coordinator is taking care about fenced producers, not allowing them. And finally, the transaction coordinator begin two-phase commit protocol. In first phase, it marks internally in his log that all the messages are in a prepare state, and then he writes, he changes the state to committed and writes commit markers in ordinary topics as well. Okay, so now we have seen how we can avoid having duplicates from the producer side. Still, consumer can read duplicates. How? Let's see within a transactional scope, the producer is sending a message. The message is written to a topic, marked, not marked yet. And then the producer sends abort. message is then marked as aborted. However, consumer doesn't know about that, so the consumer will read message anyway. And then the producer again sends a message within a transaction. This time, message is marked as committed. All great, but consumer again doesn't know about that, and we have duplicate messages on the consumer side still. So what we can do? Well, again, very easy. We can set isolation level or a property isolation level on the consumer side to read committed. And this effectively allows consumer only to read non-transactional messages and committed transactional messages. Aborted messages are skipped. That means that we still can write some non-transactional messages to the same topic, so that we have to take care about. So don't use the same topic for both handling transactions and handling non-transactional messages. No, not both of them. All right, let's see how that works. So the producer is sending a message as before. The message is written to the topic, but then it's marked as aborted. And the consumer simply skips that message. And then the producer sends a message again. This time the message is marked as committed. And this time consumer reads that message, and we end up effectively with only one message delivered. And effectively this implements exactly once scenario. And this is exactly how the Kafka Streams machinery works under the hood. So we, in a Kafka Stream scenario, we have consumer and producer enabling these properties, and then we are sending, reading records and processing records and sending them within the scope of the one single transaction, or everything is done, or everything is rolled back. However, Kafka Streams implements something else, and this is capability to save state. This is the feature that we call state machine, and we will see why it's done. So let's see how the duplicate reads in Kafka Streams still can occur. We have a read of the message is delivered, and then the Kafka Stream service dies. What's going to happen? Because the Kafka Stream service hasn't committed the message to a topic A, it will read it again. And again, a new message is written to the output topic, which is not quite thing that we desire, or at least it will be processed twice, not quite thing that we desire, right? So how the Kafka Streams machinery deal with this? Well, the Kafka Streams uses something that is called changelog. It is effectively a topic that is associated with each Kafka Stream service. And what happens is that the Kafka Stream service, when it reads and writes, also saves a state of the messaging process, right? So what happens now if the Kafka Stream service dies, right, and an error is sent to the broker from which the Kafka Stream service read the message? Well, upon restarts, first thing that the Kafka Stream service does is it rereads this state from the changelog. All right, and then when it reads a message again, it compares it with a state that was read, that has been read from the changelog. This state is then updated, and the process resumes from there, from the point when it was from the state that was last saved. And thus, effectively, Kafka Streams allows us to have exactly once delivery from topic A to topic B, even in the case of crash. So in a conclusion, we can say that Kafka facilitates transaction support in asynchronous world thanks to idempotence, transaction coordinator, and skipping aborted messages. And we also can see that exactly once in Kafka Streams are entirely possible by using state machine in addition to produce a consumer transaction support. For calls to external system within a processing cycle, still a compensation action has to be implemented to enable deletion of already committed messages. Thanks. That was all from my side. I hope that you are going to be able to find something informative from my presentation and maybe use it in your own solutions or in your own code. Thanks.